Our first of these updates is going to come from Zhang. Hong, what year would you say was like the start of your work with PETSc?
So that should be in 13 years ago.
Okay.
When I was a summer intern. At that summer, I worked with Emil on implementing extrapolated IMEX, which was somehow related to the topic today. So
Cool. All right. Go ahead.
Okay, so recently, I have added a small feature to the IMEX solvers, which were developed by Jed and Emil approximately 14 years ago. Correct me if I'm wrong. So the exact piece of code has not been updated in the past, decade. And so the last time I add new IMEX solvers was in 2012. So that was almost 13 years ago. So I'm happy, to work on this solver again and add new features to it. And this new feature made my life much easier when dealing with the fast slow systems arising in power systems. So today I would like to introduce it quickly. Hopefully it's useful for other folks who are working on similar problems. So IMEX methods are a standard technique for solving ODEs that involve a non-stiff part and a stiff part. So if you use an explicit method for solving this type of problem, the time step size is usually restricted by the stiff part. So IMEX methods can mitigate the step size restrictions by treating the non-stiff part explicitly and the stiff part implicitly. Then you end up with a scheme that is much more stable than explicit methods and less expensive than full implicit methods. It's less expensive because you only need to provide a partial Jacobian, which is the Jacobian of the function g, instead of the full Jacobian. And often in practice, people want to make this g function to be linear, so that you only need to solve linear systems instead of solving nonlinear systems at each time step. So here's an example of an IMEX, very conventional IMEX methods, IMEX Runge-Kutta methods. As you can see that you have coefficients coming from two sets of different RK methods. You have Aij from explicit RK and Aij tilde from implicit RK. But note that these coefficients are not randomly picked. You cannot pick two random Runge-Kutta methods and put them together, expect them to work. So these coefficients are designed to satisfy certain order conditions and coupling conditions, and even some additional conditions coming from stability considerations. So the textbook IMEX are usually designed to solve additively partitioned systems, such as advection diffusion equations, where we can treat the advection part explicitly and the diffusion part implicitly. So, however, in practice, stiffness may be spread across components. So what I'm talking about is the components are actually, so when I say components, that means the y1, y2 to yn, as shown in the picture. So you're partitioning the system along the vertical direction. And one example of this is geometry-induced stiffness. So when you are using adaptive mesh, you have fine regions, you have coarse regions on the mesh, and apparently these regions poses different levels of restrictions on the step size. Another example is a fast slow system, so where you have fast variables and slow variables in your system. For example, in weather models, the ocean dynamics is usually relatively slow, while the atmosphere dynamics is considered to be fast. And in chemical reaction systems, the different species may react in different rates. And similar examples come from the modeling of electric circuits and power systems as well. So apparently, you cannot apply the standard IMEX method directly to this component-wise partitioned system. But the good news is the component-wise partitioning can be converted into additive partitioning by augmenting the system with zeros. So here, if we augment zeros into this system, you have two vectors on the right-hand side. Now you have one vector which contains f and 0, the other vector contains 0 and g. And now you can directly apply the textbook IMEX solvers on this augmented system. So for example, if you apply IMEX RK, you end up a scheme like this. However, there are some issues with this trick. So first of all, these padded zeros lead to wasted flops. So imagine if you pad a lot of zeros, you're actually wasting a lot of flops in the calculation. The other problem is to solve this system, you still need to provide the full Jacobian. So you need to provide the Jacobian for the entire system. Well, this Jacobian may contain some zero blocks, but however, the structure of this Jacobian still makes it difficult to apply standard preconditioners in PETSc. Well, the preconditioner experts like Matt may have some idea, on how to precondition, Jacobians like this. But for non-experts like me, it's not convenient, to figure out a way to precondition Jacobians like this. So that's the motivation for this work. So we want to develop a new IMEX solver that can solve faster slow systems directly. So here is a general formulation of faster slow systems. We consider the system can be split into fast variables and slow variables. For the slow variables, we only have a slow right-hand side function. But for the right-hand side function, for the faster part, we allow a partitioning of two functions. So we have g and f for the right-hand side of the faster components. So the faster part is equivalent to the standard IMEX, but the slow part it just has the explicit part. So everything colored in blue will be treated explicitly. So only the red part will be treated implicitly, so in the new solver. The algorithm we use is actually quite simple. It's essentially a decoupled version of the conventional IMEX. So the only exception is at each stage, we need to update the implicit variables and the explicit variables alternatively. So the most important thing here is we need to do the update for the implicit variables first, then the explicit variable. So I have an intuitive explanation for why we do this. So presumably the slow variables usually move very slowly. So usually it's okay to lag the slow variable, but the faster variables, their dynamics actually moves very rapidly. So you don't want to lag the faster variables. So that's the reason why we want to solve the implicit variables first, then we do the explicit update. So what happens if we change the order? So what happens if we do the explicit first, then the implicit? We actually did some numerical experiments on this, and if you do the explicit update first, you end up with larger errors in the solution, and also the scheme is less stable. So this has been numerically verified that we should definitely update the faster variables first. So this process will be repeated for all the number of stages, and at the end you do a summation just like the conventional IMEX RK, and the order of equation 3 and 4 doesn't matter, so you can update them in any order. Oh, so note that if you don't have any slow variables in your system, you can see that the equation 2 will disappear from the algorithm, and you only have equation 1. So that falls back to the standard IMEX RK. So if you're using our framework, so you can also use IMEX in the conventional way if your system doesn't contain any slow variable. So to use the new solver, you need to provide a few callback functions, just like all the other TS solvers. So you need to provide a I function, which is the left-hand side for the fast variables. And you need to provide RHS function fast, which is the right-hand side of the fast variables. Then the right-hand side for the slow components. And also the Jacobian for the callback 1. The 4 is optional. So if you don't want to provide a Jacobian, PETSc will approximate it by using finite difference approximation. In addition, you need to specify, you need to inform the solver which variables are fast and which variables are slow by setting the index sets for these variables. So for example, I can tell the solver the first 4 components, they are slow variables, and the next 4 variables are faster components. And then we tell the TS their index sets. So here we are using an infrastructure called the TS RHS split, which is largely inspired by field split. So it allows you to partition the system component-wise in as many pieces as you want. And for each piece, you want to give them a name tag. So we call one piece slow and the other part fast, so that this allows us to provide the corresponding callbacks for each individual component. Here's a concrete example on how to do it in Python. So the solver is available in both C and Python. So this is a very simple 2-component ODE, and we want to treat the red part implicitly while everything else explicitly. So we have to implement the 4 callbacks. The first callback will implement the green part, and the second callback will implement the blue part, and the third one for the red part, and then the Jacobian for the red part. And the index set for this system is quite simple. So the first variable is a slow variable, so its index set is just 0, and for the second component, the index is 1. There's a more interesting example located in a TS tutorial multi-rate. So this example solves a one-dimensional advection PDE on an adaptive grid using finite volume methods with upwind slope limiters. So this example was originally designed for testing PETSc's multi-rate solvers, but minimal changes are needed to switch from the multi-rate solver to the new IMEX solver. So the only thing you need to do is just to change the RHS function fast to I function fast. So that means you are moving stuff from the right-hand side to the left-hand side. If you don't do this change, the code still works, but that means you're essentially using just the explicit part of the IMEX. You don't have anything for the implicit treatment. Then you can change the solver type to ARK IMEX and specify, I would like to use the fast-slow split by adding this option. You can also do this using the C APIs. So as you can see, the grid has fine regions and the coarse regions. The coarse grid size is about 2 times larger than the fine grid size. So this is just a toy problem. So the performance actually is not that important. So, well, if we still have time, I would like to run this problem quickly. So this is the 1D advection PDE. I want to use 60 grid points. And I don't have an analytical Jacobian for this problem, so I just do SNAS MF so that I have a matrix-free Jacobian. I want to make sure that I'm not solving the full system. So if I do KSP view, I can check that the Jacobian actually has size 30 by 30. So this is about, the regional system should be 60 by 60. So apparently this new solver is only solving a partial implicit system. Okay, so that's my tutorial today. I would like to take questions.
So in your formulation of it, you have it split into f of y fast, y slow, and g of y fast and y slow. And in the short, in your short version or your simple example, like fast, g fast was only a function of y fast. So in that one, I can see how it's clear what the split is between g fast and f fast. But what is just the general approach to understanding how you split the right-hand side between g fast and f fast?
Which simple example are you talking about?
So going forward a few slides.
Here?
So when you had one where you actually showed like just a two-component example ahead a few slides. Here.
Yeah.
So here it looks like what you have in G. So
okay, so here G is the green part. The green part is G.
The red.
The red.
Oh, sorry. The red part is G.
Yeah, and so
and
there,
the blue part is F fast.
So I'm saying that in this version, it's kind of clear that maybe the split should be the one that's only a function of the fast variables is G, and the one that's only a function of the slow variables is F. But your general form lets both F and G be functions of both fast and slow. So I'm wondering, how would someone who's trying to use this for the first time figure out what do I put in G and what do I put in F?
Yeah, excellent question. So let me come back to this general formulation. So apparently both G and F depends on Y slow and Y fast.
Yeah.
So, often in practice, you may see simpler dependencies. Like, for example, the G fast may only depend on Y fast in practice. So I'm just writing the formulation in the most general format.
Okay, it's in the general. I wasn't sure if this also came with some kind of a heuristic that people would be able to help them make that split.
Yeah. So this is like the most general formulation. When it comes to practical problems, you often see systems like that. For example, the F slow may only depend on Y slow. It doesn't depend on Y fast at all. So we have seen examples like this in practice.
Okay.
And to answer your second question, how do we split this system? I didn't mention there's a popular trick that people do in practice. So so normally we want the fast component to be represented by a linear part. So we have a matrix L plus, now we have G fast plus this F fast.
So one heuristic is if your right-hand side is split into a linear and a nonlinear, that would give you G and F.
Yes. So we want to linearize the right-hand side for the faster components, okay, so that we can avoid solving a nonlinear system. Yeah. And this L matrix is honestly, it doesn't matter that much. Theoretically, you can pick any matrix for L because whatever we put here, we will extract it from the remainders.
Okay.
So we can, for example, we can pick just the diagonal part of the Jacobian and make an L, and it works for many practical problems. We use this trick a lot in practice.
But I think one of the very common things is to divide it into local and non-local parts. Like source terms that are purely local can be done explicitly, but things that are non-local, because the things that are non-local are stiff because they have small eigenvalues like the loss.
Okay. Other questions?
I'm glad that you did this. I wanted it for a long time. So you know the IMEX implementation? That's this, but hard-coded for only the splits that the M will give you. So now we can throw that away.
Getting rid of code is the most satisfying. All right. Let's thank Hong.